Okay, yeah. So Takato had asked the question: can you define an energy operator for graphs and of our spin network states? So the answer is that yes, you can. This goes back to work that has been done by Frodin, Ghosh, and Perez, and also a very recent paper I've seen by this Finnish researcher. So this somebody from Finland, that is Javi Makela, and it's very nice because the definition of the energy is something that is again what we expect it to be in LQG, which is that it's related to the area. So it's not something that is depends on the volume. It depends on the area of. It's basically the area operator. The area operator is what you identify as the energy. And so if you want to ask what is the energy associated with some bulk region of geometry, you look at you define the surface which encloses that region, and you fix the area, the surface geometry, right? The macroscopic state of the surface geometry, and then the energy of that region contained within is simply corresponds to the that macroscopic area. So let me, for instance, show you this paper by yeah. So this is a really nice paper, Brown-York energy in spacetimes with horizon, right? And so he Jarmo Makela, I hope I'm pronouncing his name correctly, right? So the Brown-York energy, right, is defined for asymptotically flat spacetimes, and it's this quantity here, right? And second. So what he shows is that if you consider so let me highlight this. Okay, this is not highlighted. So in this paper, we shall show that in this paper, we shall show that when the two surface is just outside the closed, so he's showing this for horizons, for regions of spacetime which are enclosed within horizons, but it's more general than that, right? The Brown-York energy has a very interesting property. So there are some conditions and so on and so forth. The change in the Brown-York energy and the change in the area of the two surface S, there is the following relationship. So this is the relationship that the energy within the surface, bounded in the region bounded by the surface, can be identified with the area of the surface multiplied by the surface gravity, the acceleration. So this gives an answer to the question of how you should define an energy in the context of loop quantum gravity. But now again, this doesn't answer all questions. One still has to solve the extremization problem, which is to say that you start from some general graph state, and then you ask, well, how is there any way to show, for instance, that extremizing some sort of energy on this graph state will leave you with Minkowski spacetime or with a flat spacetime at the end of the day. That's the That's the question, right? And it's important to be able to show that that in some sense, for instance, flat space is the lowest energy state. And if one can show that, then that would be, I think, a big success for the program. So, anyways, thanks again for everybody for coming, and again I apologize for the cancellation last time. So just for the record, I mentioned that it was due to eating bad food from a nearby hotel. Right. So there are a couple of things so first of all, I just want to say that today, I think it will be the last session because I'm also feeling a little bit tired, and family is making lots of demands, and my work is also pulling upon me. So yeah, so I will talk about a couple of things. One is I'll briefly mention what the idea is behind LQC, Loop Quantum Cosmology, and some of the more iconic or seminal results in that. Then secondly, what I want to talk about is the relationship between LQG and tensor networks. And what I mean when I say that, well, the people who are working in tensor networks, they're secretly doing loop quantum gravity, what I mean by that statement. And I'll be more precise because I will show that there is a direct correspondence between something that is known as, so in the present day research in the high energy string community, there is a approach, people are following this track known as the computational complexity, which is based on Nielsen's definition, Michael Nielsen of Nielsen and Chuang definition of computational complexity. And so what I will show is that, and Nielsen's definition is based on some earlier work done by Khaneja et al. On optimization control of Hamiltonians. So on optimization of Hamiltonians. So basically trying to find the shortest path in some state space between two different states. So let's say you start from some given ground state and you want to end up with some target space, target state. Is there some way to find a sort of a geodesic in the space of states, right? And so the space of states turns out to be the same state space of LQG. And it's very nice. When I first saw this myself, I was very happy. So before I begin, let me ask: are there any questions? Okay, so you have questions. All right, and right. So let's talk about loop quantum cosmology now, because that is one of the better known aspects of the applications of LQG. Okay, so this so LQC or Loop Quantum Cosmology was something that was first sort of invented by Martin Borgewald, and so now that there are two approaches, right, to any theory, quantizing any theory of some many body system. So the first is that, so you start from the classical, whatever the classical theory is. Right. And since there are many degrees of freedom, there are two possibilities. First, you symmetry reduce. And then you quantize. So I guess it is the arrow, which should be over here. You symmetry reduce, and then you quantize. Or you go the other way. First, you quantize, and then you symmetry reduce. Right. So we have some classical theory for some many body system. Right. It can be general relativity. It can be something else. Right. So one ideally hopes that these two ways of getting to the quantum theory will commute. Right. But in general, what happens is that at least in LQG, the quantization of the whole theory, this line of research has not yet reached fruition. And back in 2000, there was very little clarity on how to, I mean, people knew how to quantize, but the symmetry reduction was not. Symmetry reduction of the full quantum state space was something that was very, very unclear. So what Martin said was that, well, why don't we take the other path and hope that what we end up with will still have some important insights to offer about the full quantum theory. Okay, so that is what he did, is that he followed this path: symmetry reduction, then quantization, and that is what gives us LQC. Of course, even in LQC, there have been a lot of developments lately, and I am also not aware of the details of many of those developments. So what I will be talking about is maybe at most something about 7 or 8 years behind the state of the art at present. Okay. So so when we want to symmetry reduce in general relativity, we have two requirements. One is that of homogeneity, and the other is that of isotropy, right? So the notion of homogeneity is that, well, the metric looks the same everywhere. So if you have the metric on some spatial manifold HAB at some point X, so we say that the manifold is homogeneous if there is some symmetry operation under which this can be mapped to the metric at some other point Y on the spatial slide. So basically the metric is the same everywhere. And more in a slightly more technical language, one would say that there exists, if you consider that there is some symmetry group which acts on S, which acts on a spatial slices, and such that for any 2 points, x, y belonging to sigma, we have y is equal to x of X, where S is an element of your symmetry group, right? Then under the action of this symmetry group, we have the following relationship, that the pullback of the metric under the action of S remains the same. So this is the notion of definition of homogeneity, right? And it's the definition that we use when we talk about FLRW metrics and so on. So then the second statement is that of isotropy. And isotropy says that the space-time should look the same in all directions, right? So if I look, so there is no preferred direction in space-time, right? And so one way to write down the requirement of isotropy is that you say that if you have two vectors in your space-time, u and v, at a some given point, and then you act with some rotation on these vectors, then this the norm of your vectors remains unchanged, right? So you look at the geometry in any direction or any pair of directions, and it doesn't change. So this is the definition of isotropy. So an example of a homogeneous isotropic metric, for instance, something we are all familiar with, right, is this, right, the FLRW metric, right? So this is both homogeneous and isotropic. Right. One way to make this inhomogeneous would be to say that, for instance, our scale factor A picks up some function, let's say on the radial coordinate, something like this. So then this is isotropic, but not homogeneous. And then if you have something like this, where you have some dependence on all of the different coordinates separately, or the different directions. So you have, let's say, three different functions, A, B, C, A t squared dx squared plus, and these functions depend on the position, right? So they have to depend on the position for homogeneity to be broken. So in general, this could be some function of r dx squared plus pt r dy squared plus c tr squared dz squared. So something like this, for instance, would be neither homogeneous nor isotropic. Right? So it's this metric that we will be talking about. Okay. Now, when you perform you can perform the 3+1 decomposition, right? So let me write down this metric again slightly, including the lapse function, and also the possibility of having an open or closed universe. So that means that we introduce this factor here, where k is equal to, there are three possibilities, -1, 0, and +1, which respectively correspond to whether your universe is open, flat, or closed. So this example is the flat universe. So if you have K is non-zero, then you can have either an open universe or a closed universe, right? And now for such a metric, one can see that the shift function is zero, right? Because if you remember, when you have this shift function and you ask a general lapse and a general shift, and you ask what is the form of the metric, it looks like this. This is the time component. Then there is the spatial component, which depends on the shift vector, and then there is a component which depends on the shift vector and the lapse vector, and there's a coupling between this time and space coordinates. And so because in this case we already are working in a set of coordinates in which we can see that there is no dx dt term, right? So that means that the shift vector is zero, right? Now, so we can write down the Hamiltonian. What the Hamiltonian for this metric turns out to be the following. This is also what we call the FLRW equation, which you get by looking at the time component of the Einstein equation, right? So you can show how this arises by doing the Hamiltonian decomposition. So let me just outline those steps briefly. You start with the Einstein-Hilbert action, right? And now we determine the Ricci scalar for our metric, the Ricci scalar for this metric. And this Ricci scalar can be expressed as follows: n square a square minus a dot n dot a n cube. Okay, so one can either plug that metric into Mathematica or look up the result in one of the many different. There are lots of nice catalogs. There is a very nice paper which is titled Catalog of Space-Times, and it's a very nice reference for many metrics. Among them, the obvious ones like this. So if you substitute this expression for the Ricci scalar in the Einstein-Hilbert action, what you get is the following: V0 by 2 kappa. Kappa is 8 pi g dt. Now this V0 is some integration over some fiducial cell. So you have your spatial manifold sigma t. You say that you pick out some finite region and you integrate over that region, and the volume of that region is V0. So of course, for the full manifold, the volume is so this is your fiducial cell B. The full volume is infinite, right? So the spatial volume. So that's one reason why we have to do this. Then the determinant of your metric, we can read that off by looking at this expression. So it's equal to this quantity, which becomes 3v naught by kappa integral by dt lapse function times minus a dot s square plus kk. So this is our expression for the action of the Einstein-Hilbert action for our FLRW spacetime, and you can see that it has the form dt nh, right? If you remember, when we do the ADM decomposition in the metric variables, we get this expression, right? We find that the Lagrangian is the sum of constraints. One is the Hamiltonian constraint, the other is the diffeomorphism constraint. This is the shift vector, this is the lapse function. So here we can see, right, that the shift vector is 0. The lapse function multiplies this quantity, and so this quantity must be the Hamiltonian. So the Hamiltonian is this a dot square by n squared plus k. Okay, 1 second, n squared. Okay. All right. So now, of course, one can also have some matter present, in which case there will be a contribution from that also, from the matter part of the Lagrangian. Now, by looking at this expression, we can ask, what is our configuration variable? The configuration variable will just be our scale factor, and then our momentum will be the conjugate variable, right? So we just find the momentum in the usual way, minus 3 by 3 v naught 4 pi g a dot by n, right? Because this is a times a dot square. So if you just take the derivative of that with respect to a dot, this is the expression. So this is our momentum variable. And then from this momentum variable, using this momentum variable, we can perform the, what do you call it, the Legendre transform, right? So if you perform the Legendre transform, which is basically just a rewriting of this expression in terms of the momentum, variable. So what you find is that the Hamiltonian constraint is, the Hamiltonian with some lapse, so I guess we should leave this out, will be 2 pi g by 3 v naught. So this is nothing more than this expression, right? You can see that you have Ka, and this is something which contains a factor of Pa squared divided by A. Okay. Now there is obviously an issue that as A goes to 0, as the scale factor goes to 0, this Hamiltonian, right, will blow up. But we will see that this will be resolved by going to the connection variables.
Deepak, I had a quick question.
Yes.
Could you go back to the expression for the Hamiltonian in terms of the canonical variable?
Yes. This expression or something?
No, the expression for the Hamiltonian, the last line that you wrote.
The last line. Okay, yeah, this one, yeah.
Yep. So if I assume that there is spatial flatness, i.e. k is 0, then it seems to me that the Hamiltonian is negative. Is it bounded below, so to speak?
All right. Well, I mean, again, is it better? No,
they are not.
The Hamiltonian is bounded below. Yeah. So I mean, yeah, that sign, negative sign, probably should not be there. And yeah, is that it?
I mean, I was reading the Hamiltonian that you wrote above also that had a negative sign in it. Is that a I mean
Okay,
here?
so let me try to give a proper answer to your question rather than just changing a sign and wishing it away. So your question is the Hamiltonian bounded from below? Well. So the thing is that, see, here we have no matter contribution as yet, right? So let me just tell you what will happen. Your total Hamiltonian will be some sum of the matter part and the gravity part, right? And this is what has to be 0, right? Okay. So the negative sign in this gravity part will be balanced out by the positive contribution from the matter part. So I haven't added a matter Hamiltonian yet. When we add a matter contribution, then the whole thing will become identically 0. Now in this case, of course, so the thing is that, see, this is 0. This is not, the negative sign doesn't matter because it's a Hamiltonian constraint. Right. So the simple answer to your question is, well, it's a constraint, so it's identically 0 on shell, and that's it. Okay. Is that fine?
Yes.
Okay. So now let me talk about the connection variables. Now we have our connection variables, and we can. So we have a connection and a co-triad, and now we know that there is a equivalence under gauge transformations. So this is the behavior of the connection, and then the co-triad will transform in this way. Okay, so now what we want to do is we want to ask that if we impose the requirement of homogeneity and isotropy on our phase space, right? Which sector of our phase space will be picked out? How will we label those points which correspond to the homogeneous and isotropic part? So once again, we say that if S is a symmetry group acting on our manifold, or actually isometry, to be more precise, acting on the manifold, and for every element S in this isometry, there exists a gauge transformation such that the pullback of the connection and the co-triad under the action of the isometry is given by the gauge transformation on the phase space, right? So this is basically saying that there is a correspondence between diffeomorphisms and gauge transformations, right? So picking out a metric which is homogeneous and isotropic, right, is equivalent to picking out the sector which behaves nicely under the corresponding gauge transformations. So how should we parameterize that part of the phase space? So we fix what we call another fiducial metric, okay, on M, and we fix the triad okay, and connection one form. So for instance, this would be so you need to have some reference, right? I mean, you need to say, for instance, that you have a flat metric, and then with respect to that flat metric, right, you define your co-triad and connection one form, and then with respect to these quantities, you can define an arbitrary any arbitrary point on the phase space related to these by some gauge transformation, and all of those points on that orbit would correspond to your flat metric or your symmetry reduced metric, whatever the case may be. So we would write down the expression for the connection one form in terms of this connection, and similarly for the triad. So actually, I've been calling this the co-triad, but we'll be working with the triad. And at the end of the day, what happens is that, of course, we make the change from the co-triad to the triad, right, just by taking the dual. So nothing is affected in that regard. This is some C, and then our so let me just write this all down, then I will tell you what is going on here. Okay. So the point is that given any A prime and E prime on M, which corresponds to this this fiducial metric, this fiducial background, let's say whether it's the flat background, or let's say you want to talk about quantization of the Schwarzschild metric, so it's the Schwarzschild background. Then, right, so all the points of the phase space which correspond to that geometry would be related to each other by a gauge transformation. And so as long as you pick one point on that orbit, you are okay, right? So this is that one representative point on the orbit of the gauge transformation. Okay. Now, of course, there can be issues related with, for example, large gauge transformation, and or you might have some obstructions, which are, I think, known as Gromov ambiguities. But again, we will, for simplicity, assume that those issues are not going to crop up here. So these are the Pauli matrices, and these are the generators of SU2 in terms of the Pauli matrix. So the only non-trivial information in this pair is contained within these two numbers, the C tilde and P tilde. So we can write down for the case of a homogeneous isotropic space-time, that the tetrad and the triad and the connection will take a very simple form, right? Labeled only by a single degree of freedom each. And this reflects the fact that, so this reflects both homogeneity and isotropy. So if you take the triad and rotate it in any direction, you should get the same. You take the frame and perform any rotation, you should your frame should not change. So that means it can only have a single scalar degree of freedom. And for the connection, you should be able to move anywhere, and the connection should also stay the same. So it can also again have only a single degree of freedom, right? So this is what a homogeneous and isotropic sector of your classical phase space corresponds to, right? And now obviously we have simplified the problem a great deal. But whenever you do cosmology, FLRW cosmology, just in the classical gravity, there also we simplify the problem down to a scale factor, right? And maybe a couple of other variables. And we don't have any problem with that. We work with that. We add perturbations around that cosmology. We do all kinds of, we calculate the CMB spectrum from that, and so on and so forth, right? And we don't have any, the assumption is that, well, on large enough scales, geometry can be described by a few, very few degrees of freedom, effective degrees of freedom. And that assumption is borne out by observations also, right? Of the CMB, for instance. So at that level, at this level, so far, that's all we are doing, right? We're just translating from the metric picture to the connection picture, that's all. But now we will proceed to do the quantization, right? And of course, this is the step that carries with it the greatest risk, because the question will be that, well, what if there are effects from the inhomogeneous and isotropic sector which would creep in, but which are being artificially left out. So again, the same question can be asked, for instance, when you do homogeneous and isotropic spacetimes in classical general relativity. That, for instance, when you calculate the CMB spectrum, if you, for example, look in one reference I like is Mukhanov's book on cosmology, he shows very nice calculations. So again, there also one can ask, well, what if corrections from the non-perturbative sector or the non-homogeneous and isotropic sectors are taken into account, what will happen? And the reason we have confidence in those calculations is again the correspondence, nice correspondence with observations, right? So again, we are working, we are rolling the dice. When it's an educated guess, right? That, well, this will describe after quantization our quantum geometry of the FLRW cosmology. Okay. And of course, this is a preliminary step. Nobody is claiming that this is the full theory, but this is what one does in the absence of a full theory, right? Okay, so now one can ask, what is the relation between these variables C and P to your metric quantities, the main metric quantity being the scale factor, and the other quantity being the time derivative of the scale factor. And then there is, of course, there is this Christoffel connection. Now, let me write this down, then I will mention what these terms are. So you remember that we have this change of variables from the extrinsic curvature to the Astiker connection, right? And that change of variables looks like this. We take this, right? So this is the Astiker-Barbero connection. So to begin with, when we perform the straightforward ADM splitting, so right, you start from your metric and momentum variable, and from that you get your triad and the corresponding momentum, which is this curvature one form, right? But then you perform this, so the triad, co-triad, either way. Then you perform this canonical transformation to get the Astiker-Barbero connection. So that's what is happening in this term here, right? So this is our Christoffel one form, and since the intrinsic geometry of the hypersurface is given by the scale factor, right? So this scale factor measures the intrinsic curvature of the spatial slices, at least in this particular coordinatization, right? One can have other coordinates also on the same manifold. So, and we know that the time derivative of the intrinsic curvature gives you the extrinsic curvature, right? So so that's where this A dot comes from. A dot is just the extrinsic curvature, right? So this is just the Astiker-Barbero connection, and this gamma is the imagery parameter. So if you set gamma to be equal to I, the unit imaginary, then you would be working with the original Astiker variables, but otherwise it's called the Astiker-Barbero connection. Okay, so up till this point, really the only non-trivial step is this one. The rest is, well, what you would expect to get if you're working with a quote unquote spherical cow, for those who know what that reference means. Then one can ask, well, what are the Poisson brackets and so on and so forth. Poisson brackets become kappa gamma by 3 V naught. And we can, now remember what this V naught is. This V naught is this fiducial volume. And actually the choice of this fiducial volume is one of the sources of a great deal of controversy at the present time between one of the creators of Loop Quantum Cosmology, which is Martin, and many other people, primarily like Abhay and collaborators. And so Martin has now like he has developed some doubts, and those are very valid doubts about what role this fiducial metric, this fiducial volume is playing. And particularly, he says that, well, can we really trust it? Trust this approximation when we're talking about when you go to very small scale factors. So let me just share that reference with you all, just for completeness sake, I guess. Okay, I can't seem to open my. It's a very recent paper. Okay, I don't seem to have it, right? So I'll put it on Zulip. And it's very, very fascinating because it's also one of the rare times that you get to see and such a conflict out in the open. You know, and perhaps there is more to it than just the scientific aspect, but we will leave all such discussions for the tabloids. So we define these rescale variables in the following way, and then we get this sort of tells you why he's put this tilde in on these other variables, because at the end of the day he wants to get rid of them. So, and now we can write down the Hamiltonian. The Hamiltonian becomes this minus 3 by kappa gamma square c square sine p root p plus, if there is a matter part, and it's equal to 0. Now there are a couple of things here. These are all constants. The gamma is the imagery parameter. It appears because of our transformation to the Ashtika variable. You have this this c square. So the c square. So c corresponds to the connection. So the c square term is this, what do you call it? Let me just go back a little bit. So yeah, you have this expression for the Hamiltonian in terms of the momentum. You have this PA square, right? And the triad or the co-triad is labeled by this p variable, right? Oh, sorry, by the okay, getting confused a little bit. Okay, never mind. Well, let me talk about the sine p. What this sine p is? This sine p comes from the fact that now your triad has a degree of freedom which is not present in the metric formulation, which is an orientation, right? So you can have a right-handed triad or you can have a left-handed triad. And the sign of P would change if you went from one to the other. Of course, to pass from one to the other, one would have to go through a degenerate geometry where the metric would vanish. So again, to not have to deal with those complications, one keeps puts this sign function in there to make sure that your orientation doesn't change. But then one can ask the question that, again, are we losing some physics by throwing away this orientation? For example, for instance, in quantum geometry, why should there be a priori any preference for a certain preferred orientation of the triad to begin with? Okay, so I'll talk about the observation between observations and LQC a little later once I've finished show you how to write down the quantum theory. Okay, and as such, you know, it's not that LQC has been verified experimentally. It is LQC has people have made various proposals for why some of the features in the WMAP or the Planck spectrum can be explained by LQC, but that is not the same as an experimental confirmation of LQC. An experimental confirmation would be if LQC predicts something, which is then thereafter found some feature which is predicted by LQC, and then it is observed. That would be, I believe, a prediction. It would go towards counting as a confirmation. All right, so let me talk about now we have this, but this is the Hamiltonian in the connection variables. And remember that when we want to go to the quantum theory, in the quantum theory, we have to define our holonomies, right? In the quantum theory, our basic variables are not the connections, but the holonomies, right? The path ordered exponentials over some edge, E is the edge, and right? So we want to ask, how can we write down this expression in terms of the holonomy of a connection? So this quantity C, which parameterizes the connection, we want to express this C in terms of a holonomy variable. So how do we do this? Okay, so you consider some curve, any line, because again, you are in a homogeneous isotropic background. So you can consider any line. In particular, let's say you consider a line which has length which is related to your reference volume V0 in this way. And then we evaluate the connection. We evaluate the holonomy along this line, right? Now this connection is just this. This connection is just this quantity, right? It's just so if you substitute this into this expression, what you will get is something like C tilde delta AI tau I NA and so on, and you can choose this NA to be any direction. It doesn't matter X, Y, Z. So then your holonomy can be written as follows. So this is the edge E. The holonomy becomes cosine LC by 2 identity plus 2 sine LC by 2 and a tau and 0. Right. So what is this? This is, if you remember from your quantum mechanics class, that when you want to calculate the element of the rotation group corresponding to a rotation around the z-axis by some theta, right? How would you do that for a spin 1/2 particle, right? You would have something of this form, theta times s of z, right? And that's exactly what we have here, right? We end up with just one element. So if you, for instance, pick this Na to be, if you say this is your z-axis, then you will single out the sigma z, the tau z component, and then this would just be the exponential of the tau z component. And that looks, when you look at this, what do you get? You get something which looks like this: cosine theta by 2. So actually, it's some e to the I theta by 2, e to the minus I theta by 2, something like this. And then the, right? Right. Or, well, if you work with the cosine signs, then you get something like cosine, minus sine, something like this. Okay. So that's basically what we are getting here. And right. So yeah, if I want to be more precise about it, yeah, this is the actual expression. Let me write that down. Along the z-axis, if we choose to go along the z-axis, we get this expression minus I sine LC by 2. Right. So we have a choice here of NA, right? NA is our direction, the tangent vector to the curve. So like I said, if we choose the tangent vector to lie in the z-axis, we get this expression for the holonomy. I sine LC by 2. Right. So this becomes e to the minus ILC by 2, 0, 0, e to the ILC by 2, which is what I had earlier. So e to the minus I theta by 2, 0, 0. So this is what this holonomy looks like. And now we want to talk about how to write down our states. How do we write down our quantum states, right? So again, we'll continue working with a single edge, and we'll ask how to write down the set of states. So if you remember, the state space is, the wave functions are written as these functions of the holonomies along the edge, right? And then we also have the fact that when we work in the spin network decomposition, our holonomies can be projected onto the different representations of the group, right? So then this can be written using the Peter-Weyl decomposition as sum of Fj Mn Dj Mn G sum over all J and Mn, right? So in the for a single edge with this holonomy, what you would get is something which looks like this: e to the I mu j c, where your sum is over j are your representations of SU2. Mu j is some real parameter and Fj is some complex number. So these are your this is the set of states for a single edge. Right. So these are just linear combinations of parallel transport along the edge corresponding to different representations, different spin labels. Okay. And I'll give you a reference in case you want to look up the precise derivation. So again, that's a book by Martin, Canonical Gravity and Application. So it's a textbook. Well, 2011. And section 6.2.1.2, Martin, being German, is very precise. So the numbering goes down 4 levels. Okay, so then we can ask what are the what is the inner product on these states, and so the inner product will be just this quantity psi1 star c, psi2 c. All right, so this is the state space. Now, actually, I'm starting to feel a little bit my stomach's starting to speak up a little bit. So I'll hurry up with the rest of this. So what we want to do is, if you look at this this Hamiltonian, we have this c square term. We want to get the c square term, right? So how do we get this c square term from the holonomy? Basically, we want to write down c square in terms of the exponentials or the trigonometric functions, right? We have this. Where do we go? We have this e to the I mu j c. So we want to write c in terms of that. So how do we do that? Well, we have this expression, right? That if you take the expansion of this function sine square mu c divided by mu square, you will get c square, right? Up till corrections of order 4th power in mu. And what is sine square? Sine square can be sine of mu c can be written as e to the I mu c minus I mu c by 2i, right? And now this is an operator which is well defined on the quantum state space. So finally, we can write down our operator for the squared connection, and it looks something like this: I mu c. We put a big hat on this. Minus I mu c. Put a big hat on this. Square over 4 mu square plus order mu to the 4th power. We can also write this equivalently as mu square plus order 4. Okay. Now we can then ask, well, what will be so this is our connection variable, and we still have to ask what is our momentum variable, right? So what is the action of our momentum variable? So if you have this momentum variable, which you remember is just this p quantity, right? The momentum variable is labels triad, and it's just this p, a single variable p. And so if in the quantum theory I say that, well, I write this operator p as the derivative with respect to the configuration variable. Okay, then this can be written as LP square comma LP square by 3 d by dc. And then I can ask, what is the action of this on my states, on these states? So, well, if you take the derivative of this with respect to c, what do you get? You get something very, very simple. There's a factor of 8 pi, so let me be careful about that. 8 pi gamma LP square by 3. You get 8 pi gamma LP square by 3 mu times pi. You just get this mu down, okay? And what is this mu? This mu again is the length of this edge. So what are these states? These states, when I say mu c, I'll write this as ket mu. So these are the eigenstates of the triad or momentum operator. Okay, and what is the physical meaning of this mu? Like I said, it's related to the length of the curve, but we can be a little bit more precise. So I remember when I wrote down this expression, I sort of skipped over, well, what is this mu? So let me mention what this mu is. So we have something called the volume operator, which unfortunately I haven't had the time to go over. So we have this volume operator when it acts on these triad states, triad eigenstates. It gives us, it has this effect. And again, I'm unfortunately don't have the time to go over how we get this volume operator. It's actually very simple and very, very beautiful. But if you have understood the area operator, then you should not have any difficulty in reading about the volume operator. For instance, in the textbook by Rovelli and Bidotto, or in my book with Sundance. So what this mu is, this is the eigenvalue of the momentum operator. So mu, if you take the square root of mu to the third power, you're basically getting the volume of some fiducial cell. So what is this mu? Mu is like L square. Mu is like the, some distance squared. Okay. So now in terms of this, one writes down the Hamiltonian, and you get. So I won't go into the details of that Hamiltonian, but let me tell you what happens. Why does the singularity get resolved, right? This is the key result of Loop Quantum Cosmology, right? And that resolution has to do with our definition of our connection operator, the C square, in terms of our holonomies. So what we have seen is that this C square can be written as exponent I delta C. Now delta is some parameter of we have fixed some particular value of mu, we're calling that delta, and ultimately we want to get rid of our dependence on delta, but whether or not that's possible, well, we'll see. So of course, when you divide by delta squared, you should ideally get rid of the dependence, but delta keeps creeping up. Okay, we'll see what happens with this delta. So what is the action of this holonomy operator on our triad eigenstates? Okay. Now, what are our triad eigenstates? Just to remind you, our triad eigenstates look like this: e to the I mu c. Right. So if you act on this e to the I mu c with e to the I delta c, what will you get? You will just get e to the I mu plus delta c. So in other words, this action will simply shift this state by an amount delta. So then, what is this c square term? If you expand out this square, what will you get? You will get something like that: e to the 2I delta c, e to the minus 2I delta c, and then minus 2, right? And then if you ask what is the action of this operator on this mu state, this term will shift the mu state forward by 2 units of delta. This will shift the mu state back 2 units by delta, and the other term will leave it unchanged. And then of course we have order delta 4 corrections. Okay. Now, what is this delta, right? So as I mentioned earlier, this delta or this mu, so the same thing, they correspond to eigenvalues of the volume operator. And the volume operator has the property that it is bounded from below, like the area operator. Which means you cannot take this delta to 0. In the quantum theory, you cannot take delta to 0. So whereas in the classical theory, you can take your connection to 0. A, right? The scale factor can go to 0. In the quantum theory, that cannot happen because of this property. Right now, this reasoning is a sort of a heuristic mix of different things. We are taking the volume operator on the full LQG kinematic phase space or the kinematic state space, which are the spin networks. Then we are combining that with this symmetry reduction. Of the classical phase space, which we are then quantizing, and then we are saying that we are taking some input from this volume operator and feeding that into this quantization, right? So again, it might seem like there is a lot of massaging going on, but again, I don't have in the short amount of time that we have I don't have, I cannot discuss in greater detail what happens. But essentially, this is what leads to the singularity resolution. And so what is the action of this Holonomy operator, right? So the physical picture is the following. Let me just show you the physical picture, okay? The physical picture is that you start with in some volume eigenstate, let's say V0. Then you act on this volume eigenstate with your Hamiltonian operator. This takes you to a state which is a superposition of a cosmology, or you can say whatever, a universe or geometry, which has a slightly bigger volume, a slightly smaller volume, and the same volume. And then if you act on this again twice, the same thing happens here, right? Each time on this, if you act with the Hamiltonian operator, what will happen? You will end up with the superposition of V0 plus 4 delta plus V0 minus 2 V0 plus 2 delta, right? For this term. And then similarly for this term, if you act on it with the Hamiltonian operator, you would get a superposition which looks like this: V0 plus V0 minus 4 delta minus 2 V0 minus 2 delta, right? And so on. So what you can see is that starting from an initial volume eigenstate, you start from an initial volume eigenstate. So this is your, let's say, the volume eigenvalue. And this is the amplitude of your state in terms of these volume eigenstates. So you start with some initial state that is peaked around some volume. Then the evolution, what it is doing is, it is taking you, this is the sort of evolution that is happening. Okay. Right. And this is reminiscent of what happens to a free particle under the effect of the Schrodinger equation, right? Now one can ask, well, how am I to make sense of this with respect to what I see around me, right? The geometry I see around me, I cannot interpret it in this sense, because what is this? This is a superposition of many different volumes, right? And I don't know how to make sense of that. So the solution is to define this notion of coherent states, which is also what you do in usual quantum mechanics, right? If you want to discuss the evolution of states without having this spreading going on indefinitely, you construct coherent states. So you can construct coherent states here also, and then you can ask questions in a more precise manner. I think there are several lectures by many other people on YouTube, and I would recommend that those of you interested in learning more about these issues can go and look at some of these lectures. And I think there should be a lecture by Abhay also on LQC. He is, of course, so there are sets of lectures by Bianca Dietrich, Carlo Rovelli, and Simone Speziale, different sets of lectures. And then probably if not on YouTube, then another great source is PERSA, the Perimeter Institute recorded seminar archive. This will definitely have many lectures on these topics. So let me just schematically sketch the evolution. What we find is, so again, this is the volume of our universe, of our coherent state, right? So we define a coherent state the same way that we define a coherent state of, let's say, the harmonic oscillator, right? So if you remember, for a harmonic oscillator, you have X and P. This is your classical state space. Then you define your coherent state as an eigenstate of your annihilation operator. And what this alpha parameter represents, it represents a point in the classical phase space X naught. It's a complex number. The real value is equal to X naught. The imaginary value is equal to P naught. And then, so the expectation value of the position operator, for instance, in this coherent state, is X naught. The expectation value of the momentum operator is P naught, right? So this gives you a state which is centered around this classical value, which is peaked around this classical value. It's a Gaussian state. So you construct similar Gaussian states which are peaked around certain volumes, and you ask, how do these Gaussian states, they evolve under the action of the Hamiltonian? So what happens is that, well, as one goes down to smaller and smaller volumes, right, eventually one reaches what would be the Big Bang, so to speak. But then again, because of quantum geometry, you go through the Big Bang. And then something very interesting happens is that you can continue past the Big Bang in the other direction. So there are different ways to look at this. One way to look at it, which is the quote unquote conventional way, is that this is a collapsing branch. This represents a cosmology which is collapsing, and it undergoes a bounce, and then you have an expansion. Okay, so this is one way to interpret it. Another interpretation, which is mine, but I don't know if anybody else has expressed a similar opinion in the literature. I haven't really searched for it, but it always seemed to be very natural to me, was that instead of thinking of this as a collapsing branch and this as an expanding branch, one way to think of it is to think of both of them. You start from some initial state, and you have two branches, but instead of saying that time goes in this direction, you say, well, no, this time goes in both directions. And here also what you have is expansion. Here also what you have is expansion. The difference is that this can be understood as, so you can view these as corresponding to different orientations of your triad variable. So you would have a left-handed universe and a right-handed universe, and this sort of like also gives a nice possible answer to or one way to look at this question of why we end up in a universe which has this asymmetry between left-handed and right-handedness, right? Which is what we observe, for instance, in the weak interactions in biology and in life in general. Which is that, you know, there are two arrows of time, and we just happen to be in one of those arrows. That's one way to look at it. Again, that is very much my own perspective. So there is a lot more to be said, but again, I have not had the time to go over all of those things. Tensor networks, Michael Nielsen's work. Let me just mention very quickly one of the things that I promised you, which was the relationship between this Nielsen and let me see, what is it? Right, so I can just write it down. So this Hilbert space of a graph, if you remember, what is the Hilbert space of a graph? It's the set of all of SU2 holonomies attached to edges. So it's SU2n, right? Modulo all the SU2 gauge transformations at the vertices, right? And this actually is identical to the, this is the same as the Hilbert space considered in the work by Khaneja and by Nielsen. And so the basic idea is that you can think of a spin network state as a single point in this state space in which you're trying to find a geodesic which connects the shortest path between an initial state and a final state. So, you know, from this perspective, the whole idea of space-time as a quantum circuit, or space-time as or geometry as quantum computation, it has existed in loop quantum gravity since the inception of the field. But of course, it is now being recognized from very different angles. What is frustrating and annoying is that you have this one group of people who has been like trying to shout and scream at the top of their lungs for many years now that look, quantum computation matters, quantum this picture of spin networks tells you that space-time behaves like, you know, a quantum circuit, and nobody gives a damn about it. And then another group of people, they discover the same thing, and then all of a sudden, Quanta magazine is writing articles about them, and so it's very aggravating because it's like sort of like discovering the North Pole, but you know, nobody really paying attention to the fact that, well, you discovered it first. But maybe, I don't know, maybe that's just the way that that history works. So anyways, I will leave it here with all my own personal opinions and aside. I think loop quantum gravity provides us a very beautiful picture of what the geometry of space-time is. And any theory of quantum gravity must necessarily incorporate these insights. So thank you all for attending these 13 lectures. I'm very grateful for your participation. Questions?
Deepak,
Yes. Yes. So my email and all. Let me just share my email. I mean, I think on Zulip we can see each other's emails in case anybody
okay.
wants to.
So I want to thank you for the lectures you have given. I have been benefited so much from your lecture.
I hope so. I hope you won't.
Actually, I
come.
didn't know LQG very much, but I have
Mm-hmm.
worked on in the topological theory.
You're right.
And that's why it is very much helpful for me.
Right.
Helpful to me.
Right.
So
Right.
I'm very grateful to you.
Thank you. I'm grateful to you for sticking through all 13 of these lectures.
Thank you so much.
Yeah. And to Takato and Mustafa, Dave Malya, Preetam, Haridas sir, who had come for some of these talks. And thank you for all of you also for showing up.
Thanks so much, Deepak. This was awesome.
I don't know. I mean, I have tried. As I've said many times, I'm not a. I can be very careless in terms of mathematics, and that can be irritating. That can be a source of irritation. But
we are all careless.
Yeah, but at the end of the day, I mean, I think that
that's why you are doing science.
Right. I try to make up for my shortcomings in terms of mathematical capability by instead trying to think intuitively. So, and I think it has paid off. Personally, it has definitely paid off. But professionally, it has paid off. It's a completely different and as yet open question. So yeah, I mean, we should continue the conversation on Zulip, and if you all are any of you are interested, I would be very happy to pursue.
So I will ask you questions after studying your book.
Yeah, please do that. And yeah, are there any questions about today's topics?
Yes. One question.
Yes.
In the expression of operator C, you had a parameter mu or delta.
That's right. Yes.
It seems dimensionful.
It is dimensionful. It is dimensionful. Yeah.
So how do you define the Taylor expansion here?
Well, I mean,
in which unit? I mean.
Well, you can always introduce some factors of h bar, I believe. I mean, this whole thing is dimensionless, right? Delta times c is dimensionless. That's what matters.
I just worried about the definition of small delta.
Right. So this delta is well, maybe I should not change the notation, but it's just this mu. And what this mu is, that, as I explained, it corresponds to the eigenvalues of this volume operator. And so Yeah, that's and so let's see, if you want to think about it in a different way, if you write down, for instance, the plane wave expansion of a state, of a momentum eigenstate, how would you do that, right? You would write down something like e to the I kx, right? And then k would be the momentum eigenstate, momentum eigenvalue, right?
Mhm.
So in this case, what you have is e to the I delta c, right? And this delta is not directly, but some raised to some power is the eigenvalue of the volume operator, which is again not directly, but it is determined by the momentum variables, which is the triad. Determined by the momentum variable. So we don't have exactly, a one-to-one correspondence, but the general sort of picture is there. Then X is our configuration variable. Right, and here C is our holonomy. And that is also our configuration variable. So very roughly speaking, that's what these are like your plane wave states, but quote unquote plane waves of quantum geometry. Yeah. And, yeah.
But this is some approximation, right? So
yeah, this is absolutely, yeah, right. This is an approximation. That's why I said that there have been many other developments. There is some improved LQC scheme and all, which I'm not familiar with. It's all very recent, of past couple of years, and I haven't had. I forget the names. I think. Anyway, I won't. I mean, you can, if you search for improved LQC, you'll see lots of papers on that. But I think that personally the most promising avenue of research is something known as group field theory. And again, I haven't had time to discuss that, but group field theory, so basically you define field theory on a group manifold, right? Just like you can define field theory on any manifold on Minkowski space. You can define field theory on a sphere. You can define field theory on a group manifold, in this case SU2. And when you look at the Feynman diagrams of that field theory, those Feynman diagrams are precisely the spin networks. So the group field theory action generates the entire, generates the spin networks. And so you can then use that action, that group field action, to study without doing any symmetry reduction, to study the full state space, how it behaves. And so what people have shown, for instance, is that you can derive these cosmologies as, and view them as condensates of this group field theory. So this is work that was spearheaded by what's his name? I'm forgetting his name now. I feel silly. 1 second. Oriti, yes, how could I forget his name? Daniele Oriti, who is at the Max Planck Institute. So this was work that was pioneered by Daniele Oriti and then people around him and others also. Stephen Geilen, Oriti's student Isha Kotecha and many others. So if you are interested in that, this GFT, you can look in Oriti. And GFT is, so actually one way to teach loop quantum gravity, rather than going through this whole ADM procedure and all, one could just start with this group field theory, right? And because that is conceptually much easier for people to work with, because everybody knows what field theory is, what Feynman diagrams are. So that is perhaps a better starting point. But again, because of various reasons, I prefer to go the other way.
Okay. Thank you for very comprehensive lecture.
My pleasure. It has been my pleasure.
Yeah, actually,
to be able to do this.
I'd rather, you didn't go into too much mathematical details, and it was very good for me. Yeah.
Yeah, no, I mean, it was good for me too, because I couldn't go into, I don't know how to go into too much mathematical detail. So any other questions?
Sir, I have a question.
Yes.
Pritam here.
Yes.
So it is from your last lecture. In last lecture, you told that if Hamiltonian...
Pritam, your voice is breaking up.
Okay, 1 second. Just. Hello? Can you hear me?
Yeah, it's better now, much better, yes.
Okay. So in last lecture, you told that if Hamiltonian acts on those graph state, according to Thiemann, it will give you the loop on the vertices, right?
Right, that's right.
Now you said that it will not give you any effective dynamics because you can shrink this loop to 0, right?
Right. I mean, you have to, if you follow the procedure strictly.
Yes. Then you give a proposal that if there are number of loops,
right.
Suppose if you take 2 loops,
right.
Then these 2 loops can intersect.
Right.
And from there, using knot theory, I think you can decompose this loop and you finally get a new graph state.
That's right.
That is the dynamics. Now the question is that those are open loops and that are attached at the vertices. Now, if an open loop is attached at any point, then how they can intersect? I mean, then the knot should be trivial, right? I mean, suppose you have 2 loops, and every loop.
No, so you're saying that if you have these loops over here, right?
Yeah, right.
Why should they intersect?
Yeah, how they are intersect? Meaning, I mean, what is the meaning
of this
intersection?
Right. The point is that, I mean, one can equally well ask, why should they not intersect? Right? Because right, if you I'm acting with the Hamiltonian operator on these 2 vertices, I create one loop associated with this vertex. Fine.
Yeah.
Then the operator acts on another vertex and I create the other loop associated with the other vertex. Okay.
Right.
Now they don't have to intersect.
Yes.
Right. But there is no reason why they should not intersect.
No, they can intersect, but my question is that is the form a knot, or I mean, what kind of intersection that was? I mean, I don't know.
So this is a linking. This is a linking, right? This is a linking. If you have,
Okay.
if you have like, it's like a link,
Okay.
right? So this forms a link. And then you can decompose that link into these different
Okay.
states.
Okay. So, what I mean, where I get this technical details about this.
Where do you get these technical details? Well, this you have to look in. Again, Thiemann gives a nice description of this Hamiltonian constraint, action of this Hamiltonian constraint. Then these things you can find in any one nice reference is the book by Baez and Munen on gauge North Story gauge and gravity, which I mentioned in Zolif in the references. Baez and Munen. And also this is true for knots. So if you know you look in for example work by Witten on the Jones polynomial and field theory and so on and so forth. He uses some like so this is how you construct a knot polynomial in general.
Okay.
Yeah. Okay, but again, like I said, this is one can very well argue that this is incorrect because I have not taken that limiting procedure which shrinks these loops to zero. Okay. All right.
Actually,
So
I
I'll
don't know is it.
Yeah.
Actually, I don't know is it right to say it here that is it possible that I can work with you in this part?
Yeah, sure. I'll be happy to work with anybody on anything.
Okay. Thank you, sir.
Yeah. Please just get in touch with me. Yeah. All right. And also, like I mentioned in the beginning of this talk, the definition of energy in loop quantum gravity is something that was given by your guide, among others, right? Fred and
Yeah.
FPG, Fred and Perez and Ghosh. So, any case, so I will end it here, and I wish all of you a very happy new year, and hopefully in the coming year, the United States will continue to be a democracy, and democracy will continue to reign over this world. Because I don't want to imagine what it would be like to do physics under a Trump dictatorship. Probably not very pleasant. Perhaps one would have to make string theory great again. And anyways, on that note, I bid all of you goodbye, and hopefully we will meet again. Cheers.